Hi everyone, my name is Tyra. I am a graduate student in the Environmental and Life Sciences program, working under the supervision of Dr. Sanela Martik. So I would like to talk to you a bit about my plan in finding the virus. And I will be introducing a new approach to rapid detection of SARS-CoV-2. So allow me to take us back about just over a year ago, all the way back to January of 2020. So at this time, some of us were likely celebrating the new beginnings of the new decade and doing everything else that we really enjoyed, yet having no idea that this could be stripped away as this big change was sneaking up on us. So in the beginning, we were hit by news of a rapidly spreading deadly coronavirus, which by March of 2020 led to the announcement of a global health crisis affecting every single person around the world. And since March until this very day, we have all been living through the ups and downs of this new norm. But on the back end of what many people have not seen are these major challenges experienced by both health and clinical professionals. At the height of the pandemic, there was a large demand for testing of millions of persons around the world, even to this day. And as time went on, with increased spread of the virus, some countries were seeing an influx of upwards of thousands to millions of samples being tested each day. And in Canada, that number was just over 77,000 tests per day in 2020. And taking a look at Ontario specifically, that total number of daily laboratory tests completed between March and December of 2020, that was also gradually increasing over time, having some of the highest numbers in Canada. So now the novelty of this virus initially forced professionals to turn to the gold standard, what we know as the polymerase chain reaction or PCR. But considering the high demand and the imminent need for these tests all across the globe, the drawbacks of these methods are being exposed. So here I highlight the trio of limitations with these PCR-based tests. Firstly, there's the need for specialized reagents to complete these tests, and that was a challenge mainly because of the limited resources. And there's also this issue with the need for a specially trained labor force to complete and analyze the results of these tests. And then lastly, something we might all be familiar with is the wait time for the results. So delaying these acquisition times mostly poses a risk for the chance of the virus spreading more and more without persons having been able to receive their diagnosis in a timely manner. And besides PCR-based tests, other viral tests that can be and have been used for viral detection are serological tests. These are often used for several different viral applications that rely on antibody and antigen interactions. And even though these tests have the benefit of providing rapid results, they do come with their challenges. For instance, there are high false negative and false positive rates associated with them that make them quite unreliable and untrustworthy. Now, many of these conventional tests that I've mentioned for viral detection rely upon either detection of viral antibodies or the detection of viral nucleic acids, but these are not ideal methods. So, for example, one of the main challenges with antibody-based tests, like those serological tests that I've mentioned, is that they are not ideal as indicators for active infection, and these targets are not usually detected until about 7 to 21 days after an infection has occurred. And so delayed detection then means that early diagnosis is not likely, which could be important information for helping to prevent continued transmission of this virus. On the other hand, an issue with nucleic acid-based tests, such as those PCR-based tests, is with the possibility of collecting insufficient amounts of genetic material from suspected samples. And this can lead to inaccurate data from tests, including receiving false negative results. So considering the challenges with these conventional methods, it is quite obvious that alternatives to these approaches are needed. And ideally, what we want is something that can provide rapid, reliable, and accurate results all in one. So there are other special elements of the virus that we can make use of for the purpose of viral detection. And what I'm referring to are the coronavirus related antigens or proteins. And the virus has four main structural molecules that can be used as targets for the detection of this virus. Of particular interest for us is this spike protein or spike antigen. And this is the part of the virus that is mainly responsible for the attachment to the human cell, which in turn causes what is classified as an infection. And as you can see illustrated here, it is also located right on the surface of the virus, which can be beneficial in many ways for the purpose of targeting the virus. And in my research, I use small molecules called aptamers, and these aptamers are intentionally designed to directly bind to select targets, such as the desired coronavirus S antigen. And when the aptamers come into contact with the target antigen, a complex is formed. And these aptamer antigen type systems, I should mention, have been used in similar design for some other viral infections like dengue, Zika, and influenza, which you might also have heard of. So in these times especially, these systems are beneficial because they can provide high sensitivity since, like I mentioned, these aptamers are designed specifically to bind to an intended target. And by targeting viral antigens, there is also the possibility for early diagnosis and the benefit of using various sample types for diagnostic testing. My work uses localized surface plasmon resonance or LSPR for analysis. And simply put, this is a technique that can measure small changes in optical properties of a surface in response to the occurrence of binding between two or more molecules, such as the binding between that coronavirus antigen and the aptamer that I am using. And there are several benefits of using LSPR methods over other conventional tests. So for instance, the system has the potential to be automated, which makes it less labor intensive. And this also offers real-time measurement and a fast response time that is typically just a few minutes, which helps to minimize delays in the acquisition of the results. As the premise of this work relies on a simple protocol, and that is collection, sample preparation, and then finally detection. So now I'll take you more in depth through getting to know how this testing process will work. So this is the setup. This testing surface is curated specifically to screen for and identify the COVID-19 antigen. And so we can think of this as a hunt for the bad guy. Everything will take place on this small stage, which is just a glass surface, and this is just about the size of a US penny. It is essentially the designated platform where all the action takes place, and this chip sits here just under the hood of this instrument. And so the platform is made of small gold particles which are attached to that glass surface. And depending on the mission of the mission protocol of the aptamers, this gold surface can be modified to fit the particular circumstance. And so in this case, our aptamers serve as some of the most highly qualified agents in the field because they have been trained specifically to identify that COVID-19 spike antigen. And the designated location of all the aptamers will be on top of this gold surface. And so the preparation and the execution of this process, or this mission, I should say, is actually quite neat and simple. So here we start with our gold-coated platform that will be tuned to fit our mission. And one configuration of this platform that is useful to us is what I will refer to as a Biotin Streptavidin chemistry. And so we would first start off with a layer of biotin protein that just coats that gold surface. And then we would apply a layer of streptavidin protein right on top of that. And so the idea here is that these biotin and streptavidin molecules are very much like best friends. So they have a high affinity towards each other and will form a strong, unbreakable bond when they are in the presence of one another. And this chemistry then can be used to the benefit of this mission. Next, the aptamers are introduced to the platform by a simple injection of the sample solution into the instrument, as you can see that I'm doing here. And basically how this works is that all the aptamer agents on the missions get to have an assistant with them. And this is the only way that they would be permitted to stay on the prepared platform. And for this mission specifically, the aptamers work closely with their biotin assistants that are attached to them at one end. And so in this way, the attached biotin will bind to that streptavidin that is already on the surface, which in turn allows the aptamer agent to stay on the platform by association. And once the aptamers get in and onto the surface, the mission is a go. And so a follow-up injection of the patient sample to be tested will allow any coronavirus antigens and other invited parties just to trickle through the crowd. And just as they are trained to do, the aptamer will quickly identify the antigen and it'll capture it. And at that point, the mission is complete. So immediately with each injection, this is the information that we get. Real-time, quick analysis. So this obvious increase in the signal signifies some change happening at the surface. And in this case, that change is a successful attachment of the molecules following each injection. So in the first instance, the signal increase shows the attachment of the aptamer to the surface, and that plateau indicates that a sufficient amount of the aptamer agents are present and staying to complete the mission. Then following this, the introduction of that S1 antigen shows a significant signal increase, meaning that the target antigen was captured. And this is typically a very quick response time, taking just about 10 minutes to complete the entire mission after all the aptamers are in place. And this particular S1 aptamer agent is also quite capable of distinguishing the S1 antigen apart from other relevant components. And this is great because it gives us an idea of where on the spike antigen the aptamer prefers to bind, and that this interaction is specific to that molecule. So for instance, I'll show here that when we have the aptamer set up and ready to go, and we have BSA, which is a non-coronavirus related antigen, or even the coronavirus S2 antigen present, neither of them can be captured by that aptamer because this is not what it was trained to do. However, when we have the RBD antigen present, we see a completely different response. Now the RBD component is actually a part of the S1 subunit of the spike antigen. So what happens here is that there's some binding between the RBD and the aptamer, but because the aptamer does not bind predominantly to just the RBD component, this attachment is not very strong, which means that even though the RBD initially binds, it may easily be attached after a while. And this is in contrast to having the entire S1 component present. So in this case, the S1 antigen is captured by the aptamer and it stays there, which in turn translates to a very high Lspr signal being achieved. And this comparison therefore determines that the S1 antigen and the S1 aptamer complex is the ideal setup for this rapid test, and this system is what I will be basing the remainder of my research on. So what happens next? One benefit of using this Lspr method is the potential for reusability. Luckily, this is not a one-time use platform, and we can use the same testing surface for several consecutive measurements. So essentially, once we have the S1 antigen captured by the appropriate aptamer, we are able to refresh the surface through a simple regeneration step. And this is done with the use of a specific regeneration molecule, which basically reverses that reaction, allowing for the bond protein to be released from the custody of the aptamer agent, making the surface clear and ready for measurement of another patient's sample. So let's now take a look at an example application. So here we have an individual experiencing COVID-19 symptoms and in need of immediate testing. So their options are to provide a non-invasive saliva sample, or they can go ahead and provide a blood sample to test serum. And based on my research, when samples of spiked artificial saliva and serum albumin are tested, a signal recovery of over 90% was achieved for each application. And this just suggests that testing in different sample matrices has no effect or influence on the aptamer's ability to detect that S1 antigen. And this means that this test protocol can be similarly applied to real-life samples collected from suspected COVID-19 patients. So as I conclude, I would like to highlight that there is a lot of promise around the use of Lspr apta sensors or Lspr aptamers and the aptamer antigen systems for the application of viral detection. And so the design setup that I have explained is merely a proof of concept for the use of this aptamer antigen system as an alternative method for rapid detection of SARS-CoV-2 in patient samples. Ideally, this platform would be capable of providing quantitative information about the coronavirus-related measurements, and with some simple and easy modifications, this can be similarly applied to other viral antigens. So I would just like to conclude here and thank and acknowledge my supervisor, Dr. Senela Martik, as well as the Martik Lab group members for their support and contributions, and also Nicoya Life Sciences, the industrial partner on this project funded by NSERC Alliance COVID-19 grant, and the ENLS Graduate Students Program at Trent University. And lastly, thank you all for listening.